After this lecture, okay, there will be one more lecture on electrostatics, and after that, the chapter of electrostatics is finished. Okay, we'll be starting on the chapter of capacitor. We'll be starting from out there. So what I'll do is, after completing this chapter of electrostatics, I'll go back to collision. Okay, where I left off. So in collision, we'll complete the collision. And one more thing, some of you might have a problem with this large picture format. So the large picture format was introduced due to 3D. This chapter is very 3D in nature. So instead of visualizing showing you how the 3D works, okay, just blackboard representation of 3D would be very intuitive in nature. So wherever 3D diagrams or wherever large format is required or large picture format is required, I'll be just reverting back to this. Otherwise, the remaining of the lecture will be black and white. Okay, so follow this lecture. Okay, the dipole. In this lecture, we started about or we discussed topic about dipoles. Okay, okay. In this question, okay, there are two plates: a positively charged plate of radius r and charge density sigma, and a negatively charged plate of radius r and charge density minus sigma. They are separated by distance L. You have to find out the electric field and potential at distance x from the midpoint between the plates. Okay, this is distance x. See, you have to find out the potential and electric field out. So in the previous question, okay, I already have done the potential and electric field due to a pair of rings separated by distance L. Okay, at distance x from the midpoint, the potential was how much? K Q L cos theta by x square sec square theta, isn't it? And which can be or which was later simplified to k q l x by x square plus r square to the power 3 by 2, where r was the radius of the ring. Okay, theta was nothing but distance from the point to the midpoint between the plates. This was angle theta. Okay, so how do I integrate a plate or how do I integrate a disk? Disk is nothing but integration of rings from 0 to r, isn't it? So if I take an elemental ring out here, okay, so elemental ring of radius r, okay, what is the potential due to the elemental ring? So potential due to the ring is equals to, I have to use the same formula, isn't it? The same formula will be used out here, which is nothing but k q l cos theta or k dq. dq is nothing but the charge of the elemental ring. Okay, l cos theta by x square sec square theta, x square sec square theta, isn't it? Now what is the charge in the elemental ring? The charge density into area of the ring. So dq is nothing but dq, or elemental charge in the ring, is nothing but charge density sigma into area of the ring. Area of the ring is nothing but 2 pi r dr. So if I do write this, v ring, okay, is equals to k l cos theta. Okay, and I'm writing dq right now. dq is sigma 2 pi r dr divided by x square sec square theta, x square sec square theta. Okay, now to integrate r and dr, isn't it? R and dr. Now what did I say? See, the hypotenuse will vary as I go from r is equals to 0 to r is equals to capital R. Okay, so whenever hypotenuse is varying and the vertical is varying, always convert everything in terms of x and angle theta, isn't it? So if I take an angle theta out here, okay, can I say r, or r is equals to, or tan theta is equals to r by x tan theta? See, this was r, no? This was the elemental ring. Suppose, assume or just imagine this elemental ring to be this situation. Okay, so out here what can I say? This distance is x, Okay, and this is hypotenuse or under root of x square plus r square. So can I say tan theta or tan theta is equals to x by r? See, tan theta is nothing but perpendicular, sorry, r by x, not x by r. R by x, I made a mistake out here. Tan theta is equals to r by x. Okay, tan theta is equals to perpendicular by base or r by x. So out here r is equals to x tan theta. So I have to substitute out here r by x tan theta. This r will be substituted by x tan theta. And the second substitution is I have to differentiate this term with respect to d theta. So dr by d theta is nothing but x sec square theta, or dr is equals to x sec square theta d theta. So I have to substitute dr out here. So when I do that, or potential due to the elemental ring, due to the positive elemental ring and negative elemental ring. Okay, potential out here was found out due to the positive and negative both the rings, no? Okay, so if I substitute, let's take KL sigma 2 pi, KL sigma 2 pi, all the constant. The remaining are cos theta into cos theta. Now I am left with r into dr. So r is nothing but x tan theta, and dr is nothing but x sec square theta d theta, x sec square theta d theta, divided by how much? Divided by x square sec square theta, x square sec square theta, isn't it? Sec square theta and sec square theta will get cancelled. X into x is nothing but x square, this x square and this x square will get cancelled. Okay, so we are left with how much? Let's see. So we are left with KL sigma 2 pi cos theta tan theta into d. Tan theta is nothing but sin theta by cos theta. Okay, so sin theta by cos theta, and this cos theta and this cos theta will get cancelled. So cos theta into tan theta is nothing but sin theta. So this is sin theta. Okay, and this theta I'll write down out here. Understood? Instead of writing it forever. So potential due to the elemental ring is nothing but given by this value. Now to find out the potential of this pair of disk, okay, I have to integrate this, isn't it? From acha, I have converted the elements from r to theta. Okay, so what are the limitations? At r is equals to 0, or at this point, what is the value of theta? Theta is equals to 0, no? Okay, so at theta is equals to 0 to theta is equals to capital R to theta is equals to, so when r is equals to means when theta is equals to at this point, what is the value of theta? Theta is nothing but this value. Okay, so 2r is equals to theta. Theta is equals to this entire value for the extreme r and x. Okay, this angle would be theta. Understood? So now just let me, V ring is nothing but case KL sigma 2 pi. What is the integration of sin theta? Cos theta. Now let's put the limit. Okay, limit is nothing but from theta is equals to 0, as theta is equals to 0, okay, to theta is equals to r, to theta is equals to theta. At theta is equals to this extreme value. Okay, what is the value of cos theta? The value of cos theta is nothing but x by capital R, no? X by under root of r square plus h square. Okay, so cos inverse x by under root of x square plus r square. Okay, so integrate from theta is equals to 0 to theta is equals to this value. Okay, this entire value. Fair and fine. What is the potential at theta is equals to 0? At theta is equals to 0, no amount of charge was there, no? So potential was equals to 0. Okay, and what is the value at potential is equals to this what? This capital R, V. So if I do this one, potential due to ring, is equals to KL sigma 2 pi into cos theta. The value of cos theta is nothing but x by under root of x square plus r square. X by under root of x square plus r square. Okay, and the value of 0. Okay, cos 0 is nothing but 1. So minus of cos 0 or minus of 1. Understood this one? Okay, so this is the potential of the disk or potential of the pair of disks of positively charged and negatively charged. So let's simplify this equation out here or simplify this parameter out here. Okay, this parameter can be written as, or potential due to disk can be written as KL sigma 2 pi. Okay, now what is the value of KL sigma 2 pi? See, KL sigma 2 pi. K is nothing but 1 by 4 pi epsilon naught, no? So 1 by 4 pi epsilon naught into L into sigma into 2 pi. So 2 pi and 4 pi would get cancelled by 2. So it would be sigma L by 2 epsilon naught. So this entire term would be nothing but sigma L by 2 epsilon naught. So it is nothing but sigma L by 2 epsilon naught into x by under root of x square plus r square minus 1. Understood? So just let me erase this one. One more thing that I should have told you is, instead of converting everything, if you take in terms of algebraic terms also, but dq is equals to 2 pi r dr, okay, convert x is or r is equals to x tan theta. Okay, so if you take r is equals to x tan theta in this equation, everything will come like this only. Okay, it doesn't make a difference whether you take the component later or you take in algebraic terms. Okay, out here after writing down the algebraic equation, if you take r is equals to x tan theta, your equation will come out to be like this one. Okay, so it doesn't matter if you take or if you differentiate out here or if you use the diagram and take the potential according to this formula. Understood? The main thing to remember is whenever hypotenuse is varying, okay, the hypotenuse is varying, no, always convert the parameters into x, okay, and theta. X should be, or the length should be constant, the angle theta should be variable, and it is much easier to integrate that way. Understood? See, now I already found out the electric field or electric potential at point x. Okay, now how do I find out electric field? I simply apply electric field is equals to minus dv by dx, and the direction of electric field will be along the direction of x. That means when I'm differentiating with respect to x, the direction of electric field will be along the direction of x. So into x cap. X cap means nothing but this direction or a unit vector along this direction. Okay. So electric field is equals to minus d. What is the value of d? Sigma by 2 epsilon naught x by under root of x square plus r square minus 1. Okay, minus 1 with respect to dx. Okay, now what I must do out here is I must take all the constant term outside, isn't it? So electric field would be minus sigma by 2 epsilon naught into d x by under root of x square plus r square minus 1 divided by dx. This can be separated into two parts. Two parts means, see out here, d of x square plus r square into, not into, minus of d of 1 by dx, isn't it? This minus 1 out here, I just separated that minus 1 out. Understood this one? Now this 1 is a constant, no? So the differentiation of constant is always equals to 0. So this will be equals to 0. Okay, so I'm erasing this one. Understood this one? Now I have to differentiate this term with respect to x. Fair and fine. I can write this term as x into x into 1 by under root of x square plus r square. And when I differentiate this, I have to take a, then I have to differentiate this term, plus I have to take this term, then I have to differentiate this term. So first I'm taking x constant, and I'm differentiating under root of or x square plus r square to the power minus 1 by 2, minus 1 and minus 1 by 2. Then after differentiating this term, I have to go inside and differentiate x square. The differentiation of x square would be 2x, understood, plus 1 by under root of x square plus r square. I'm taking this constant and differentiating x. Okay, if I differentiate x, what will happen? Differentiation of x is nothing but 1, understood. This 2 will get cancelled, x and x would become x square. Okay, so out here I'm just, and I'll write this minus at the front. Okay, I'm writing this minus at the front. It was multiplied by minus, no? Minus 1 by 2 minus 1 is nothing but minus 3 by 2. Minus 3 by 2. Okay, and this plus I'm writing out here. Okay, plus 1 by under root of x square plus r square. Wait and find the under root of x square plus r square can be written as 1 by 2. Okay, and this can be written as 1 by x square plus r square to the power 3 by 2. 1 by x square plus r square to the power 3 by 2 minus 3 by 2. When it goes to the numerator, it becomes 3 by 2, no? So our numerator becomes minus x square plus 3 by 2. Now look at this term. Okay, can I multiply the numerator by x square plus r square and denominator by x square plus r square? See out here, if I rewrite this term just neatly, okay, I'm just rewriting the same thing again. X square plus r square to the power 1 by 2. Now at the numerator I multiplied by x square plus r square, and the denominator also I multiplied by x square plus r square. Okay, just I think there is a problem with gaps out there. Okay, the problem with gaps. It's 1 by x square plus r square to the power 1 by 2. Okay, so out in this section, okay, this section I'm just multiplying x square plus r square in the numerator, and x square plus r square to the power 1 by 2 was already there into x square plus r square, isn't it? I can do this one, no? This term is equals to this term, and why have I done that? To make the denominator equal so that I can calculate easily. Okay, so x square plus r square to the power 1 by 2 plus 1 is nothing but to the power 3 by 2 to the power 3 by 2. So this term will become x square plus r square divided by x square plus r square to the power 3 by 2. Fair and fine, no problem up till here. Now when I take the denominator common out here, okay, or is equals to minus x square plus r square divided by x square plus r square to the power 3 by 2. Okay, minus x square plus x square gets cancelled, so I would be left with plus r square divided by x square plus r square to the power 3 by 2. Or my electric field vector is given as minus sigma by 2 epsilon naught, okay, into r square by x square plus r square to the power 3 by 2. Understood this one? One more thing, I forgot to pull L out here. So L would be out here. See the previous thing, okay, sigma L r naught. Now what you are going to do out here is electric field and potential due to a pair of oppositely charged plate. Okay, and the kind of plate that is that I'm doing out here is infinite plates. Okay, so electric field and potential due to a pair of oppositely charged infinite plate. So suppose I have an infinite plate out here. Okay, the plate is infinity in z direction, and the plate is positively charged. Okay, with charge density or planar charge density sigma. The question I have out here is what is the electric field out here? Okay, on the left side of the plate, and what is the electric field out here? Okay, to find out the electric field, how does the electric field due to a charged plate or infinitely charged plate look like? The electric fields are parallel to each other, that goes away from the plate, isn't it? Okay, the electric fields look somewhat like this. Now, if I take in some amount of charge, and if I find out the electric field due to this charge, I can find out what is the electric field at each point in the space, isn't it? So if I take this amount of charge, I have to draw a Gaussian surface. So my Gaussian surface would be somewhat like this. We have already done it inside class for infinite plates. Okay. So if this area, the middle area, and this area is same, let this area be A. Okay. So this area is also A, and this area is also A. So if I apply Gauss law out here, the Gauss law says that electric flux is equals to electric field into area. What is the total area of this Gaussian surface? A plus A, which is equals to 2A. So electric field into 2A is equals to Q inside by epsilon naught. The electric field in this Gaussian surface would be in this direction. Electric field in this Gaussian surface would be in this direction. Okay. What is Q inside? Q inside is nothing but charge inside this element, which is nothing but charge density into area of the plate, or charge density into area of the plate. So if I take these two equations, E dot 2A is equals to sigma into A by epsilon naught, which should be equals to A and A will get cancelled, or electric field is equals to sigma by 2 epsilon naught. So out here electric field is equals to sigma by 2 epsilon naught, and out here also electric field is equals to sigma by 2 epsilon naught. Okay, so this much you have understood. Now let's take a negative plate of same size. Okay, and the charge out here is minus sigma. Okay, so the electric field in this direction would be in this direction, and electric field out here would be in this direction. If I take the same Gaussian surface, electric field out here would be sigma by 2 epsilon naught, and electric field out here would be equals to sigma by 2 epsilon naught. And the electric field will look going towards the plate, or parallel line going towards the plate. Fair and fine. Always remember, these are infinite plates. Okay, the size of the plate is infinity. So whenever I'm Acha, I'll tell you what the size of, or what does infinity signify in physics. Okay, now what I'll do out here is I'll take two plates, this positively charged plate out here, okay, positively charged infinite plate, and negatively charged infinite plate. Okay, and they are separated by distance L. Fair and fine. My first question is, what is the electric field out here outside the plate? What is the electric field inside both of the plates? What is the electric field inside or outside this negative plate? Okay, so the first thing is I'll try to derive the electric field out here. The electric field due to left of positive charge, okay, due to this plate in out here would be nothing but sigma by 2 epsilon naught towards left direction due to the positive charge is equals to sigma by 2 epsilon naught, or electric field due to positive charge. The electric field due to this negative charge towards the right of the plate would also be sigma by 2 epsilon naught towards left. So electric field due to the negative charge at the same point, okay, would also be sigma by 2 epsilon naught. So the total electric field due to these two positive charges, or due to this positive plate and this negative plate, is nothing but sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is nothing but sigma by epsilon naught, isn't it? So electric field out here is nothing but sigma by epsilon naught. Okay. Now my question is, what is the electric field out here? See, if you take this, or if you take the electric field out here. Due to the positively charged plate, electric field will be in this direction, which is equals to sigma by 2 epsilon naught. And due to negative charges on the right hand of the plate, or on the right hand side of the plate, the electric field at the same point would be sigma by 2 epsilon naught, but on the opposite direction. So the electric field due to the positive charges and the electric field due to the negative charges cancel out each other. Okay. So the net electric field on outside the plate would be 0. Understood? So the net electric field outside this plate would be 0. A similar kind of things will happen out here. Electric field outside this plate also is equals to 0. Okay. Now one important aspect to note out here is what is the potential out here, or what is the potential in between the plate, outside the plate. Okay. So to understand potential, the first thing you need to understand is there exists nothing called absolute potential energy. Okay, there exists only called differential potential energy. So whenever an absolute potential is asked, what is the potential at this point due to this charge Q? Okay, so what you are actually saying is what is the potential energy difference between our unit column kept at infinity to unit column kept out here. Okay, or what is the negative of work done in bringing a unit column from infinity to that point. Understood? So potential is nothing but work done against conservative force. So whenever absolute potential is asked, I always have to first figure out what is the datum line, or what is the reference line, or what is the reference line where potential is considered to be 0, isn't it? So for example, there is a positive Q charge out here. What is the potential out here? The potential out here is nothing but work done in bringing a unit column from infinity to this point. So I have considered the potential at infinity to be 0, potential at this point to be kq by r. Understood? So whenever you are asked about potential energy or absolute potential energy, the first thing you have to remember is what is the datum line, or what is the reference line, okay, or where is the potential energy 0. Okay. So for a plate of charge, okay, potential energy at infinity also is equals to 0, potential energy at this infinity also is equals to 0. Okay, fair and fine. Now let me first figure out, or before finding out absolute potential, let me first figure out what is the potential difference between this positive charge and this negative charge. That means what is the work done in bringing a unit column from this point to this point. Okay, so if I start from infinity, okay, there is no electric field out here. So work done by electric field is equals to 0, change in potential energy equals to 0, or change in potential is equals to 0. Now if I bring a positive unit charge from this point to this point, okay, electric force on unit column is nothing but electric field, which is given by sigma by epsilon naught, isn't it? And that displacement is equals to L. So work done is equals to field into displacement. So potential is equals to minus field into displacement. So the potential difference between positive and negative charge, okay, or final potential minus initial potential, is nothing but minus sigma L by epsilon naught. Is a potential difference between these two, or V final minus V initial. Understood this much? The potential difference between the positive plate and the negative plate is nothing but sigma L by epsilon. Okay. And as I take this charge outside this plate, even out here electric field is equals to 0, work done by electrostatic field is equals to 0. So potential difference would always be equals to 0. Now suppose I say what is the absolute potential out here or out here or out here. Okay. So to figure out absolute potential, you first need to find out what is the reference line, or where in this setup I have to find out the potential is equals to 0. Okay. So usually potential at infinity is taken as 0. But in case of a positive charge plate, see the midpoint between the plates. Okay. If you keep a positive 1 coulomb charge out here, okay, the potential due to this plus plate is kq by r. The potential due to this negatively charged plate is minus kq by r. So the potential at the midpoint is equals to 0, no? So the midpoint is usually kept as a datum line for a pair of plates. Okay, this is datum line or reference plane, okay, or base plane. Out here the potential is equals to 0. I potential is equals to 0. Okay, the electric field is in this direction from positive to negative charge, and the electric fields are parallel to each other, that I've already said. Okay, Now what is the work done, okay, in bringing this positive 1 coulomb from this point on midpoint to the positively charged plate is nothing but sigma L by 2 by epsilon naught. This is the electric field, this is the displacement. Displacement is nothing but L by 2, isn't it? So the absolute potential at positive plate would be given as how much? Electrostatics sigma by, or electric field is equals to sigma by epsilon naught, and displacement is given by L by 2. Out here, let's find out the work done is positive or negative. The electric field is in this direction. So work done by electrostatic force is negative because displacement is opposite to the direction of force, isn't it? So if work done is negative, potential will be positive, isn't it? Or potential difference will be positive. Why? Potential energy is nothing but negative of work done, okay, by conservative force. Similarly, if I want to find out the negative potential energy at the negative plate, okay, it would be nothing but sigma L by 2 into epsilon naught. 2 into epsilon naught. I'm just rewriting this sigma L by 2 epsilon naught neatly. Okay, sigma L by 2 epsilon naught. So the thing that you have to remember out here, whenever there is infinite plate, okay, the potential at the center is equals to 0, potential at the positive plate is equals to sigma L by 2 epsilon naught, and potential at the negative plate is equals to sigma L by 2 epsilon naught. Now since, see, if you move from this plate to out here, okay, is there any electric field in this space? No, isn't it? There is no electric field in this space. So the potential change or change in potential energy would not be there. So if change in potential energy is not, would not be there, so the potential at this point is equals to potential at this point. So potential at any point outside the plate is also given by V plus is equals to sigma L by 2 epsilon naught. Why? Because since there is no electric field, since there is no electrostatic force, therefore there will be no change in potential energy. Understood? Similarly, elect or potential outside the negative plate would be nothing but V minus is equals to sigma L by 2 epsilon naught. Okay, understood? Since there is no electrostatic force, there is no change in potential energy. Understood? See, understand this concept carefully. Change in potential energy is nothing but negative of work done by electrostatic force. Understood? Okay. So all I'm trying to say out here is if there are two infinite plates, okay, the electric field at any point between the plates would be sigma by epsilon naught. The electric field outside the plate would be 0. The electric field outside the negative plate would be 0. The potential at the datum line would be 0. Okay, potential at any point outside the positive plate would be sigma L by 2 epsilon naught. Potential at any point outside the plate or outside the negative plate would be minus sigma by 2 epsilon naught. Minus out here, minus out here. Why minus? Because out here electrostatic force is doing positive work and change in potential is nothing but negative. So you got that much. Okay. So this much is understood. Now you might have one specific question, sir, why suddenly have taken the reference line from infinity to center of the thing? Okay, for this case of scenario, okay, just remember the potential is taken at in between for ease of calculation. Okay, for further ease of calculation. Okay, there's no ground and hard and fast written rule that you have to take the potential at this point is equals to 0, or you have to take the base at means potential at infinity is equals to 0. Potential difference matters more than the absolute potential itself. Okay, understood? In this case, I have taken the reference line to be midpoint between the charge plates. Understood? And one more doubt I might have is what happens if the plates are not infinity? Okay, so in physics, whenever I talk about infinity, no, that means suppose there is an infinitely charged plate. Okay, what I mean by that was the distance at which I have to find out the electric field is very small compared to the size of the plate. Okay, see, for infinitely charged plate, if this charge plate is not infinite, it would look somewhat like this. Okay, it would look somewhat like this. It would be mirror of each other. Okay, means there will be a little bit diverging outward. But if I see very close to the plate, okay, very close to the plate, what happens? The electric field are parallel to each other, no? all the electric fields are parallel to each other. So that is what is happening out here. Understood? So for infinite plates, the electric fields are parallel to that plate. Okay, and that won't be happening if the size of the plate is not infinity. If the size of the plate is not infinity, the electric field will be a little bit diverging. Understood this much? And after this, we'll go to the next question. Okay, see, now in this question, okay, there is an infinite plate. Okay, the top infinite plate is positively charged and the bottom infinite plate is negatively charged. They are separated by distance L. That means the thickness of this plate is L. Okay, and in the middle of the plate, a circular disc is cut out. We have to find out the electric field at this point X. Okay, at this point X. So I can easily apply the principle of superposition. And what does principle of superposition says? The electric field due to this setup is nothing but electric field due to the parallel plates. Okay, the first plate is positively charged and the bottom plate is negatively charged. Okay, minus the electric field due to a circular pair of discs. The top plate is positive charge and the bottom plate is negatively charged, isn't it? I have to find out the electric field at point X due to a infinite plate. I have to find out the electric field and potential due to a circular disc of radius r at point X, isn't it? This is equals to X. This is also equals to X. Okay. Now from the previous lectures or previous question, the electric field outside the plate is equals to 0, isn't it? What is the potential at point X? Potential at point X is nothing but sigma L by 2 epsilon naught, isn't it? Due to a positive charge, this sigma L by 2 epsilon naught, because below the negative charge, it would be minus sigma L by 2 epsilon naught. Fair and fine. Similarly, in the previous question, what is the electric field due to a disk? The electric field to a disk of radius r, okay, is given by E disk is equals to sigma or minus sigma L r square by 2 epsilon naught x square plus r square to the power 3 by 2, isn't it? That is the electric field at this point, and electric field is in this direction or along the x. Electric field is in this direction. Fair and fine. And what is the potential out here? Potential out here is nothing but sigma by 2 epsilon naught into x by under root of x square plus r square, okay, minus 1. This was the electric field and this was the potential. Fair and fine. Now total electric field due to this setup at point X, we do nothing but electric field at point here due to infinite plate and electric field at this point due to this circular disc of radius r. So net electric field is equals to how much? Electric field due to infinite plate is nothing but 0 minus of electric field due to circular disc is nothing but minus sigma L r square by 2 epsilon naught x square plus r square to the power 3 by 2. So if I calculate that, it is nothing but sigma L r square by 2 epsilon naught x square plus r square to the power 3 by 2. Similarly, potential or net potential due to infinite plate out here is nothing but sigma L by 2 epsilon naught sigma L by 2 epsilon naught minus, see, what is the potential due to a disk out here? Sigma by 2 epsilon naught into x by under root of x square plus r square minus 1, isn't it? Now if I evaluate this, okay, this sigma L by 2 epsilon naught and this minus 1 would get cancelled. So net electric field is equals to, or net potential outside the plate is equals to sigma, okay, out here also there would be sigma L, no? There would be sigma L. Yeah, I forgot to put a L out here. Okay, sigma L. So sigma L by 2 epsilon naught. I forgot to put a L out here. Okay. So this sigma L by 2 epsilon naught and this minus 1 into sigma L by 2 epsilon naught would cancel out each other. So we'll be left with sigma L by 2 epsilon naught into x by under root of x square plus r square. So this was the problem of 3.4. Okay. Now in this question, there is an infinite charge carrying wire. Okay. And a dipole is kept on front of this infinite charge carrying wire. We have to find out the total force on this dipole. The charge density of the wire is given by lambda. And basically there are three variation of the same problem. Three variation means there are three orientation in which the dipole is kept. Okay. So this is part A of the question. So in part A of the question, the dipole is kept along the wire. Okay, this is dipole at distance r. In part B of the question, the dipole is kept along the radius. Okay, and part C of the question, the dipole is kept perpendicular. That means if this is the charge carrying wire, the dipole is kept in this axis. Okay, if this is the axis of charge carrying wire, the dipole is kept in this axis. Okay, a z direction. So I'll show the dipole vector by this. Okay, or a vector going towards you. Understood? Now we have to find out the force on this dipole. See, dipole means positive charge on the arrowhead and negative charge on the tail of the arrow. Positive charge out here, negative charge out here. Positive charge towards yourself and negative charge at the tail of the arrow. Now what is the electric field out here due to infinite charge carrying wire? 2k lambda by r, and the force is nothing but q into electric field. The force on the positive charge is 2 lambda or 2k lambda q by r, or q is the charge of the positive end of the dipole. Similarly, negative on the dipole would face 2k lambda q by r, isn't it? Because negative charge gets attracted towards the wire. Fair and fine. And the lines are, or the electric field lines generated due to this positively charged are parallel to each other. I've explained this in that Gaussian theorem. Okay, how Coulomb's law and Gauss law relates to each other. Fair and fine. Okay, so the net electric force on the first case is equals to 0. See, 2kq lambda by r, 2kq lambda by r, they cancel out each other. So net force is equals to 0. On part B of the question, okay, if this is distance r towards the center of the dipole, okay, let the distance between the positive charge and negative charge be 2l. Okay, so the force on the positive charge is in this direction, which is equals to 2k lambda by r. What is the distance? Distance is nothing but r plus l. So r plus l, and the force on the negative charge is nothing but 2k lambda by r minus l, or this much distance only, r minus l. Okay, into q, because force is equals to electric field into charge. Okay, so net force is equals to 2k lambda q by r plus l minus 2k lambda q by r minus l, which is equals to, I can take 2kq or k lambda q common, k lambda q common, 1 by r plus l minus 1 by r minus l, isn't it? R minus l. If I take LCM, it would be r plus l into r minus l. So it would be r plus l minus r minus l. And I have taken LCM common of r plus l into r minus l, isn't it? So r plus l into r minus l is nothing but r square minus l square. R square minus l square. This plus and this r would get cancelled. You are left with l plus l. See out here. This L will get added to this L, so it would be 2L on the numerator. So it would be 2L. Okay, and you have to take an assumption out here. Since R is much greater than L, that means L will get nullified to 0. Assumption is R is much greater than L. So out here L will be transferred to 0. On net force is equals to 2k lambda q into 2L divided by R square, isn't it? Q into 2L is nothing but dipole vector. So Q into 2L is nothing but dipole vector. On net force on the dipole is equals to 2k lambda p by R square. Okay. Now the third diagram. Okay, this diagram. If I rotate the wire in Z plane, see, the initial orientation was like this, no? This was the wire, but the plane was the dipole. So if I rotate the whole setup by 90 degrees, that means the wire would be towards you and away from you, and the dipole would be from up to down. Understood? So if I rotate this entire setup, okay, but this is the wire or linear charge carrying density lambda, and the dipole is given by this vector. So out here it is positively charged, out here it is negatively charged. Out here the force would be how much? In this direction. Okay. Okay. This is L, this is also L, isn't it? So out here force would be 2k lambda by R. What is the value of R? Under root of R square plus L square. Under root of R square plus L square. And out here in this direction the force would be towards the charge. It would be 2k lambda by under root of R square plus L square, isn't it? And one more thing, I forgot the Q. Force is nothing but electric field into charge. Okay. Now if you observe something out here, the magnitude of this force and the magnitude of this force is same. Okay. If you take the horizontal component, okay, see, if I take this angle as theta, that means what? This angle would also be theta. That means this angle is also theta by symmetry, and this angle is also theta. So if you observe closely, the horizontal component of force due to positive charge and the horizontal component of force due to negative charge cancels out each other. Whereas due to the vertical component, okay, the vertical component of force adds each other up. So what is the vertical component of force? Or F total out here would be vertical component of force, or 2 into C. If I say the vertical component of this force is nothing but 2k lambda cube by under root of R square plus L square into sine theta. The vertical component of force is sine theta. Okay. Okay. So if this angle is theta, this angle is also theta, no? This angle is also theta. So that if due to one of the charges, the vertical component of force is this much. Due to two charges, the total vertical component of force would be this charge, or vertical component of this charge plus vertical component of this charge, which is equals to into 2. That means this value is added twice. Understood? Okay. Now let's check what is the value of sine theta. Sine theta is nothing but perpendicular by hypotenuse. So sine theta is equals to how much? Perpendicular. What is perpendicular? L by what is hypotenuse? Under root of L square plus x square. Sorry, L square plus R square. R is the distance from the wire. Okay. Now if I substitute the value of sine theta, F total is equals to 2k lambda cube by under root of R square plus L square into 2 into 2 into sine theta. Value of sine theta is nothing but L by under root of R square plus L square. Okay. Now see, Q into 2L is nothing but the dipole. So Q into 2L becomes dipole. Okay. R square plus L square into R square plus L square is nothing but R square plus L square under root of R square plus L square whole square. So this would become whole square. Okay. And if I whole square a square root, the root gets cancelled. Okay. The roots will get cancelled. So total dipole is equal, total force is equals to 2k lambda p by R square plus L square. Fair and fine. See, the previous method that I have showed you is a little bit cumbersome. That means suppose two dipoles are given. You have to find out this negative charge, this positive charge, this negative charge, this positive charge. So the calculation would become cumbersome. There is one more formula in which I can find out the electric field due to a force on a dipole. And that formula is given by force is equals to, or force vector is equals to dipole vector dot dE by dr. Okay, understood? Dipole vector into dE by dr. So in the first scenario, okay, this is our F is equals to, see, is the electric field changing with respect to R? The electric field at this point would be 2k lambda by R. The electric field at this point would be 2k lambda by R. So there is no change in electric field, no? As I go from here, that means the dipole is kept at same electric field, isn't it? So E into dp by, sorry, P into dE by dr. P into dE by dr. But dE by dr becomes 0, so the net force out here also becomes 0. Okay, net force out here is also 0. In the second question, this is r vector. Now in this question, dE by dr varies. But net force is equals to dipole vector into dE by dr. Okay. Now as I go in the direction of r, the electric field changes, but the value of r increases. So force is equals to P into, what is the value of E? 2k lambda by r, isn't it? Divided by dr. If I differentiate this one, F is equals to P into 2k lambda by r square. Okay, there will be a minus out here. Minus means the force is acting in this direction. Okay, net force is acting in this direction. Why? See, if you apply common logic, see, positive charge is more far away from uh, this wire, no, and negative charge is towards the wire. So the attractive force will be greater than the repulsive force. So net force is nothing but P into 2k lambda by r square, which is same result as the previous question or previous slide that I showed. Okay, in this slide or in this part C of the question, okay, see, the value of r changes out here also as I go through the dipole. The value of r changes, and the direction of angle the dipole makes with r vector also changes. So, okay, so for this kind of problem, instead of complicating the situation, you have to find out electric field as a function of theta and r, then find out d by dr. So instead of all that complications, just put positive charge, negative charge, and draw it by free body diagram. Okay, this was to just show you there exists another formula for force on a dipole, which is given by P dot dE by dr, or rate of change of electric field with respect to r. Okay, and the direction of this vector is nothing but r cap. Okay, sorry, not dot dE by dr. Okay, dE by dr should be a scalar quantity. Understood? Apply common sense, if this was a dot product, then force has to be scalar, no? So dE by dr is nothing but change of electric field with respect to r. Change of electric field with respect to r. Okay, out here force would be found out by simple Newtonian mechanics. Understood? The mistake I made out here was making this a dot product. See, if you apply common sense, if I do dot product, then force has to be scalar, no? So dE by dr is nothing but rate of change of electric field along the direction of r. Okay. See, the formula I taught you before comes out, or comes in utility out here. Out here in this question, there are two water molecules. Okay. First water molecule and second water molecule. They are separated by distance 10 nanometer or r. Okay. We have to find out the force acting on these two water molecules, or force of interaction between these two water molecules. You already know from chemistry that water is a dipole, okay, or water is a polar molecule. The first question I have out here is, what is the electric field out here due to this dipole? So axial component of electric field is equals to how much? 2 kp by r cube, isn't it? And force acting on this dipole should be equals to P into dE by dr, or force is equals to P into 2 kp by r cube. Now d 1 by r cube by r. So force is nothing but 2 k p square into d of, not d of, 1 by r cube is nothing but minus 3 into r to the power minus 4. Or force acting on one dipole to the other is equals to 2 k p square into minus 3 by r to the power 4. Or force is equals to 3 into 2 is nothing but 6 minus 6 k p square by r to the power 4. And by Newton's third law, if this dipole exerts the force of this value on this dipole, equal and opposite reaction would be applied on this dipole. So force out here is equals to how much? 6 kp square by r to the power 4. One thing to note out here, see, minus signifies the direction of force is in this direction. Why? See, positive charge out here and negative charge is out here. Negative charge is out here and positive charge is out here. See, the attractive force between positive and negative is strongest out here. Okay, strongest between any of the four charges. There are four interaction, no? Negative, 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 positive, positive, negative, and positive, positive. The strongest force out here is nothing but attractive force between positive and negative. So the force out here would be in this direction. Similarly, the force out here also would be in this direction. So force on the first dipole is in this direction, force on the second dipole is in this direction. Okay, and the magnitude of force is nothing but 6 kp square by r to the power 4. Now suppose instead of same water molecule, if there were different dipoles p1 and p2, same formula, electric field is equals to 2 kp1 by r cube. Okay, force out here is equals to p into, or p2 into dE by dr. So what I'm trying to say is, if there are two dipoles p1 p2 separated by distance r, the electric field out here due to first dipole would be E axial is equals to 2 kp1 by r cube, and the force out here would be minus 6 k, or let me just write it, p2 into dE by dr, or force is equals to minus 6 kp1 p2 by r to the power 4. By Newton's third law, the force acting on this dipole would be in this direction, the force acting on this dipole would be this direction. Both these forces have the same magnitude. Okay, now just put the value of k. K is equals to 9 into 10 to the power 9. Put all the values as given in the question and find out the answer. Okay, k out here is nothing but 9 into 10 to the power 9. P is nothing but given as 0.62 into 10 to the power minus 29. R is given by 10 nanometer, or is equals to 10 into 10 to the power minus 9 meter. Okay,